Greetings and welcome to the complete lecture for Chapter 17 of Chemistry 222, and I'm glad to have you here. This chapter is going to look at kinetics, which is the study of speed when it comes to chemistry. And speed is important. If you're like me, once in a while you can get impatient about things, and oh my goodness, it would be nice to know if you could speed things up. Or sometimes if you wish to slow things down, it would be nice to know about that too. So in this chapter, we're going to do exactly that in terms of chemistry. We're going to see about the factors that make a reaction go faster, the factors that can make a reaction go slower. We're going to look at how reactants go to products and all other kind of cool things. Kinetics is an important chapter. We talked about thermodynamics earlier. Thermodynamics is a great way to tell if a reaction is going to occur or not, and that's very powerful. However, kinetics is a great complement because if a reaction is going to occur, but it takes millions and millions of years, that's not going to be very helpful. So the study of kinetics will tell us approximately how long it takes for a reaction to go to completion, which is also super powerful. So anyway, sit back, relax, and let's see what this chapter has to offer us. So in chemistry, thermodynamics, which is enthalpy and other terms that we'll look at more later, are useful because they can tell if a reaction will be product or reactant favored. Product favored means the reaction will occur, and reactant favored means the reaction will probably not occur. But it doesn't give us any information as to how fast the reaction goes from reactants to products. And again, if a reaction is going to take millions of years, who cares if it's going to go or not, because that's way past our lifetime, if you know what I'm saying. So kinetics is the study of how fast reactions go. A rate is essentially a speed when it comes to chemistry. So reaction rates are basically the speeds of reaction. And we're going to see how to make the reaction go faster and slower. And along the way, we'll also learn about how reactants go to products. And that's through something called the mechanism. Up to this point, we have only looked at reactants and products, the beginning and the ending. But have you ever wondered what happens in the middle? That's where a mechanism becomes really helpful. A mechanism will allow us to investigate the path, if you will, that reactants go to products in order to have that happen. And it's really fascinating. We'll see some really interesting kind of chemistry along the way. So anyway, it's kind of cool. We're going to see what happens between the reactants and products. We're going to see what happens within the arrow between the reactants and products. It's a pretty cool chapter. Now, the speed, as I said earlier, of a reaction is called a reaction rate. So every time you hear rate, just think speed. And speed is no big deal if you're, say, driving a car or something like that. You know how many miles per hour you're going or kilometers per hour if you're in Canada. A reaction rate will be similar. It's the speed of a chemical reaction. And the rate of reaction is just, again, telling you how fast it's going to go from reactants to products. And this is going to be part of the tool we'll need to control the chemical reaction to figure out what makes it go fast and what makes it go slow. So a rate is going to be, for chemistry, how much of a quantity of reactant or product changes over a given amount of time. And again, the speed of a car is usually how many miles are driven per hour, something like that. That's how speed is expressed. So units of your car will be miles per hour, kilometers per hour if you're in a metric country, stuff like that. In chemistry, though, we don't have miles to travel, or kilometers for that matter, but what we do have is moles per liter used per second. It's quantity used per unit time. And so usually the time is in seconds, and usually the speed is listed in moles per liter per second. All right. Molarity is the number one unit when it comes to chemistry. It's used more than anything else. And so most of the time, the rates, the speeds are listed in how many moles per liter are being used per second. So if you see something like you do there in the lower right-hand side, where it says rate equals minus delta H2 over delta T. Let's look at that a little bit. So first of all, things in square brackets, like the H2, that's moles per liter, all right? So that would be saying the moles per liter of H2. And then delta, like we've seen before, delta is final minus initial. So if the final time is T2 and the initial time is T1, then delta H2 will be the change of the H2 concentration concentration at time 2 minus the H2 concentration at time 1. And likewise, delta little t on the bottom will be delta time. So it'll be the time at time 2 minus the time at time 1. So anyway, this will all make sense here in a little bit. It's a little bit weird, but that's what it means. Just remember delta, final minus initial. And then if you see things in square brackets, that means moles per liter. A chemical reaction, the speed of a chemical reaction, is a little different than your car, all right? Because you have to know how the concentration of the reactant is decreasing because reactants are used up. But sometimes you can also think about how much product is appearing because products appear in a given reaction. So when you write something like we did for that H2 thing on the bottom, if it's a reactant, we need to put a negative sign in front of it. And this is a little strange, but let me try and explain to you. H2, if it's a reactant, its concentration will constantly be going down because in any chemical reaction, reactants are used up and products are created. So the change in H2, the final time where H2 is measured minus the initial time where H2 is present, that's going to be a negative number, all right? So the delta H2, delta for any reactant is going to be a negative number. So scientists put a negative in front of reactants to make those negative signs cancel out, and you end up with a positive rate. So number one thing to learn so far in this chapter is that when you're talking about the speed of a reactant, you need to put a negative sign in front of it because the delta reactant concentration is a negative number, and negative times negative makes a positive, which everybody likes. So anyway, just realize that if you have a speed of a reactant, all right, you need to put a negative in front to make those negative signs cancel out. So this H2 plus I2 making 2HI is a great example of how scientists need to think about speed. Now, if you have a car, there's like only one speed, the speed of the car. But in chemistry, it would be nice to think about the speeds of reactants, how fast they're disappearing, and also the speeds of products, how fast they're appearing. And in order to make the negative of the reactants go away, we put a negative sign in front of those, like we talked about. But there's another thing that you have to think about as a chemist, because for every one H2 that's being used up, you're going to make 2 HI. So that stoichiometry, that 1 to 2 ratio is also important. So if you use up 1 mole of H2, you're going to make 2 moles of HI. And if you use up 2 moles of H2, you're going to use up 4 moles of HI, etc., etc. So chemists also have to deal with the stoichiometry of each chemical in the speed. So this is a little weird, but bear with me here. If you're going to talk about the speed of a reaction, it's nice to think about the speed in terms of both the reactants and the products. But there are two things you need to do. And if you look down there at the bottom, this is a great example. We have some kind of random A reacting with some kind of random B, and that makes big C and big D on the right. But also notice there's the little a, little b, little c, etc. Those are the stoichiometric coefficients. Now, in order to make the speed of the reactants be equal, make sense to a speed of a product, there's two things you need to do. And number one, we've already talked about. You need to put a negative sign in front of the reactants. So big A and big B are reactants, and they both have a negative. You'll see in front of C and D, there's a positive sign. You don't change those because the change of a product will always be positive. The change of a reactant will always be negative. So that's the first thing. But the other thing you need to do is you need to go 1 over the coefficient for any reactant or any product. So you can see that all those things down there have a 1 over little a or 1 over little b, 1 over c, etc. That's just to make all of the speeds the same, because HI in the H2 plus I2 making 2HI reaction, that's appearing twice as fast as the H2 and the I2. So the speed of HI appearing would be twice as fast, if you will, as the H2 disappearing. So you put 1 over the stoichiometric coefficient in front of it, and those will all be taken care of. Now, if everything I've just said in the last minute or so is gobbledygook, and I understand, here's the punchline. Number one, when you're talking about the rate, if it's a reactant, put a negative sign in front of it, and if it's products, then you just put a positive sign in front of it. But number two, the other important thing is that you always want to have 1 over the stoichiometry in front of the chemical. So the balanced reaction will tell you the stoichiometry. If it's just a 1, of course, you can ignore it, but if it happens to be a 2, then it would be 1 over 2, or 1 over 3 if the stoichiometry is 3, stuff like that. So let's look at an example of how you can figure out the expression for a rate in chemistry. And remember, what we're doing here is we're figuring out the speed, but we're trying to relate a speed which makes sense for reactants to a speed that makes sense for a product. And so along that way, what we're going to do in this problem is we're going to talk about average rate and the individual rates. So what we have here is a reaction where hydrogen peroxide is reacting with iodide, I-, and some acid, H+. And it makes what's called the triiodide ion, I3-, and some water. But here's the important part. In the first 10 seconds of the reaction, the concentration of the iodide dropped from 1 molar down to 0.868 moles per liter. And we can use that information to calculate the average rate of this reaction during this time interval. We're also then going to take that average rate and we're going to figure out the rate of change of concentration of the H+, i.e. we're going to find a specific rate, a specific speed for another chemical, another reactant, which is H+ during this interval. Okay, so first of all, the average rate, we're going to use that expression up there in the upper right. And because this is a reactant, iodide, I- is a reactant, we'll use one of the left-hand ones. So notice therefore the rate of the little a, it's -1 over a, change of the delta A in moles per liter divided by delta T. And we're going to do something like that for iodide. Now again, because iodide is a reactant, we have to put a negative sign in front of it. And the other thing that's important here, there's a big 3 in front of the iodide in the reactant chemical equation. So we're going to have a 1 over 3 in front of that to make sense. So initially, the rate is going to equal -1 over 3, the delta I- concentration over delta T. And again, iodide is a reactant, so that's why the negative is there. And there's a 3 in front of the iodide, so 1 over 3 is what we'll put there. And then the rest of it is delta I- over delta T. If this would have been a product, we would not have used a negative sign. It would have been just positive. But either way, whatever the stoichiometry is, those big numbers in front of the chemicals, you want to put that in front of it. Now, delta, as I said, is final minus initial. And we're going to do final minus initial for the iodide concentration. That's going to be the final concentration 0.868 and the initial concentration 1.000. And the delta time, the final time will be 10 seconds and the initial time will be 0 seconds. So if you throw all of that in your calculator, you get a speed for the iodide of 4.40 times 10 to the -3 molar per second. Now, notice that the 0.868 minus 1, that would have been a negative number. Reactant concentrations are always going down. So final minus initial will always give you a negative number. And that's why I've been hyping so hard that if it's a reactant, put a negative sign in front of it. The negative sign will neutralize the reactant concentration values, which are negative, and make it an overall positive speed. So the average rate for this chemical reaction, 4.40 times 10 to the -3 molar per second. So every second, this reaction is using up 4.40 times 10 to the -3 moles per liter. That's what it's saying. Now, in the second part of this reaction, we're going to do delta H+ over delta T, and it's going to look somewhat similar. The H+ has a 2 in front of it, so instead of 1 over 3 like we had for iodide, we're going to use 1 over 2. And H+ is a reactant, so there'll be a negative in front of it. So the rate for this one, rate will be -1 over 2 delta H+ over delta T. So again, notice it's a reactant, so we put a negative in front of it. It's 1 over 2 this time because H+ has a 2 in front of it, not the 3 like we had last time. So this is what we have. Now the rate, the number, the expression on the left, that's 4.40 times 10 to the minus 3. So we're going to rearrange this expression for delta H plus over delta T. So if you do that, you get minus 2 times the previous rate, minus 2 times 4.40 times 10 to the minus 3, and that comes out to be minus 8.80 times 10 to the minus 3 molar per second. Now, while 4.40 times 10 to the minus 3 molar per second, answer A, that's the speed of the overall reaction. It can be used for reactants and products, but that's the overall speed. The minus 8.80 times 10 to the minus 3 number we just calculated, that's the speed for the H plus disappearing, essentially. It's how fast the H plus is disappearing. So reactant concentrations are always going to be negative, so the speed of the reactants by themselves will always be negative, like the 8.80 times 10 to the minus 3. However, the overall rate and the rate of the product, if you want to figure that out, those numbers will always be positive. So it's a little strange, but it's nothing you can't handle. And again, if you have questions on this, reach out to me or reach out to the Learning Success Center /Avid Center, and they can help out as well. This is a graph showing N2O5 decomposing, and there's actually different kinds of rates that are possible. And if you had calculus under your belt, or maybe you have calculus under your belt, integration and differentiation are really great tools to have for figuring out rates. But you don't have to have calculus under your belt, certainly for Chemistry 222. So what we're going to do in this class is just talk about average rate, all right? And the average rate is just the easiest way. You just use it as an overall speed for the overall reaction. It's good to go. But if you study kinetics more in the future, you might see some of these other kinds. They can be pretty powerful. So here's a question. It says, what's the average rate of this reaction over the first 2 minutes? Okay. And you can see here there's different concentrations on the y-axis, and the time is on the x-axis. So the first 2 minutes then, you can see on the x-axis, there's a 2 right there and a 0 right there. So if you go up to where the 2-minute part is, it's right there. And if you go up to where the 0 time is, it's right there. So what we're going to do here, rate is going to be the average change in the concentration over time. Now this is a reactant. Notice how those numbers are getting smaller as time goes on. So the reactants, we always put a negative in front of them. We're going to assume the stoichiometry is 1 since we have no better idea. So the rate will be a negative for the reactant, and then it'll be the change in the reactant at 2 minutes minus 0 minutes. So for this problem, it looks like that's going to be roughly at 2 minutes, roughly 1.7, and roughly at 0 minutes, roughly 3.4. So it'll be 1.7 minus 3.4 or something like that. And then in the denominator, you'll have the change in time. So that'll be 2 minutes minus 0 minutes. It'll be 2 minutes. So if you calculate this, then you'll have negative for the reactant, 1.7 minus 3.4. Those are the numbers for the concentration at 2 minutes and 0 minutes. And then on the denominator, you'll have 2 minus 0. That's delta T, delta time for the time elapsed. 2 minus 0, throw that out on your calculator, 0.85 molar per minute is the speed. The average rate will always be a positive number. Having a negative number would be like turning products into reactants, and that's a little advanced, shall we say, for this course. But in our class anyway, the overall average rate will always be a positive number, but you can see how this is. So you can use a graph to figure out the concentration values, divide them by the time values. Good to go. This is a trick that can be handy, and it's an approximate time elapsed for a reaction. And this isn't always totally right, but it gives you an idea. So remember that all the rates that we've seen so far have been some kind of moles per liter per unit time, usually per second, all right? Well, if you have a rate and you have an amount of compound that you start with, you can solve for time here and figure out approximately how much it's going to be. So as an example of this, 4.3 times 10 to the minus 6, we'll say that's the speed, the molar per second. And the amount of compound we're starting with here is 0.00250 molar. It would be nice to know approximately how long it's going to take to react. So if rate equals concentration A over time, let's solve for time. Time's going to be concentration divided by the rate. And if you do that and you throw those numbers in there, so you can see on top is the amount of the reactant we started with divided by the speed that it's going, it should take roughly 580 seconds for it to complete. Now, I have used this to high success sometimes in some of my research I did back in my graduate school days. I had some reactions that would take hours and hours to go, and I didn't want to sit there and wait there, so I would figure out an approximate amount of time for them to happen. I would then go and do other things, go to the library or do whatever, go to a movie, who knows. But anyway, they took a long time to go. But anyway, they gave me a rough guide. And, if it says it's going to take 580 seconds, you want to start watching about 500 seconds in case the sig fig rules are weird or something. But it does give you a rough idea as to how long a reaction will take to happen. So the things that make those speeds bigger and smaller, faster and slower are important questions to consider when you're a chemist. And so here are just kind of an overview of what happens. Small molecules tend to react a lot faster than large molecules. Small molecules, you can usually just use them as is, but larger molecules, sometimes there will be a target zone, and getting the right chemicals in the target zone can take a little bit longer, so that's kind of a general trend. Gases tend to react faster than liquids in general, and liquids tend to react faster than solids. Again, this is general, but it has to do with orienting things. Ions generally react faster with molecules. If you have more surface area, you can have a better chance and faster reaction than if it's like a concentrated source. I'll show you a cool video of this here in a little bit. If you have higher concentrations of reactants, that means you'll have higher collisions and faster reaction rates that way too. Generally speaking, temperatures will make particles collide faster. It also gives them greater kinetic energy, so that makes it faster. And catalysts are substances that can make a reaction go faster without being used up themselves. And that's pretty cool. We'll talk about catalysts more here in a little bit. But if you have a catalyst, it should make your reaction go a lot faster, which is neat too.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution, the reaction is much more vigorous. Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
Both of those test tubes have hydrochloric acid, but in one test tube, the concentration of HCl was 6.0 moles per liter, and that's a lot bigger than 0.3 moles per liter. And you can see how the magnesium metal just reacted super fast with a 6 molar HCl and very slow with a 0.3 molar HCl. So on the right-hand side there are two graphs corresponding to the different HCl concentrations. And the HCl graph with 6 molar concentration, which is on the bottom there, you can see it's almost a straight up and down line. It's very, very fast reaction. The whole reaction was done, say, in less than 50 seconds. On the other hand, the 0.3 molar HCl, you can see it took closer to 400 seconds to get to approximately 0 magnesium. So the amount of the concentration does make a big difference. The bigger the concentration value, the faster the reaction in general, which is kind of a cool thing.
On the plate is a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Solids, as we saw in the intermolecular forces chapter, are very dense. The atoms are very close to each other. And when you have a solid, then you only have the outermost level of the solid exposed to whatever reactants there are. So, for example, there you tried to use a Bunsen burner on solid lycopodium powder, which is some kind of powder from mushrooms, apparently. Anyway, it doesn't hardly react at all. But if you spray the lycopodium powder through the Bunsen burner, man, it's like they use this for magic tricks, apparently. Sometimes it's very kind of flames and stuff like that. Those little particles of lycopodium react a lot faster than the bulk is, because the bulk only affects the outside. Also, in this set of pictures there, you can see two effects of iron. On the left-hand side is an iron nail in O2, and it does react, but it's very slow. On the other hand, steel wool, which is essentially iron, but very, very low density, it reacts super fast and will burst into flames when you have it in pure oxygen. So again, the amount of surface area can make a big difference in terms of the speed of the reaction.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
In a different chapter, we use this video to talk about stoichiometry, how to figure out amounts of products being created, stuff like that. We'll come back to this here again because this is a great example of a catalyzed reaction. Hydrogen peroxide, H2O2, does break down to water and O2. So if you buy it in the store, it's in a brown bottle. You're supposed to keep it out of the sunlight in a refrigerator to keep it from breaking down. In the presence of a catalyst like manganese 4 oxide, MnO2, not manganese dioxide, but anyway, the MnO2 then makes the H2O2 decompose very, very fast, as you could tell. It's so fast that it's amazing, really, and it breaks down to H2O and O2 right away. And this is an example of what's really called a positive catalyst, which is what most catalysts are. It makes a reaction go a lot faster than it would be without a catalyst, and that's most of the time what catalysts are for. However, you should know that there is a term called a negative catalyst. A negative catalyst, although not as common, do slow a reaction down. And sometimes that's important too. If you want a reaction to go slower, a negative catalyst will make that go slower. All catalysts, whether they're positive or negative though, catalysts will be used up in the reaction and they'll be regenerated at the end. So as an example, in the H2O2 example, you can see the water on the bottom is kind of murky. That darkness is from the MnO2. And if you took the water and MnO2 and you dried it really well, you could reuse that MnO2 in another set of reactions. Catalysts, in theory, just keep going and going and going on and on and on. They usually have some kind of final point where they no longer work because of some weird chemical pathway, but they can go on for many, many transformations, which makes them very powerful.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
Warmer temperatures make reactions go faster, and we'll talk about why that's the case in a little bit in this chapter. But if you need a reaction go faster, you can warm it up, and that will certainly make it go a lot less, as you could see from that food dye example. A chemist's rule of thumb for a reaction is that by increasing a reaction temperature by 10 degrees should basically double the speed of the reaction. So as an example of that, let's say you did a reaction at 20 degrees Celsius and it took 5 minutes. Well, if you then did the same reaction at 30 degrees, roughly 10 degrees higher, it would take half that time, or 2.5 minutes. So that can be kind of useful. That's not totally followed all the time, but it's a rough guide and stuff, especially if you have a reaction where timing is critical. So all of these factors are going to go into what's called a rate law. And a rate law is like a law, if you will, an equation that's specific to a given reaction. And it tries to help chemists and scientists to figure out things that make the reaction go faster and slower, and also perhaps provide ideas on how the reaction can go faster or slower. Now, you must determine the rate law experimentally, all right? Despite all the AI and supercomputing kind of stuff that's available available now, rate laws must be determined in the lab. All right, so this is a lab-based phenomena, which is kind of cool. And the rate of a reaction will be proportional to the concentration of each reactant raised to some kind of power. And I'm sure that's not super clear, so I'll give you some examples of that. So the rate law is an important tool to figuring out why reactions go fast and slow, and also to provide some ideas about how to make them go faster and slower. So for a random reaction of capital A going to products, where capital A has a stoichiometry of little a, you can write a general rate law like as follows. The rate equals the rate constant K, which is also something you have to figure out through experiment, times the concentration of capital A to the n power. And n is called the order of the reactant. Now for Chem 222 and Chem 223, n is going to be 0, 1, and 2 only. All right. Outside of these classes, you might see different values for n, but in our classes, it's going to be 0, 1, and 2 only. So if you know the rate order and you know the rate constant K, then you can find the rate, the speed of the reaction for any set of combinations, which is really cool. And only reactants and sometimes catalysts will appear in the rate law, no products. So this is kind of the basis here of determining what goes on. So here's what's going on. The rate is the speed, all right? And you can measure that by figuring out changes of concentration over time, stuff like that. But to know why that speed is as it is, it's nice to know about the order of the reactant. That makes a big difference. And you do need the rate constant K. K is a value that's independent of concentration. It does change with temperature, but rate constant Ks are just numbers, and we'll talk about how to do all of this here in a little bit. In Chemistry 222 and Chem 223, those orders will be 0, 1, and 2 only, and they call them 0 first or second order or zeroth. I don't really like that term, but that's what they call it. But anyway, the effect of 0, 1, and 2 is just like in math. So anything to the 0 power, like 3 to the 0, 10 to the 0, anything to the 0, is just 1. So any reactant to the 0 power will just be equal to 1. Rate equals K, the rate constant. What we're going to see a lot of, though, are first order reactants. Now, anything to the first order is just itself. So as an example, 2 to the first power is 2, 10 to the first power is 10, etc., etc. So rate equals K times A. That would be a first order reactant. We will see some second order reactants, though. Second order reactants affect your rate in a big time way. It's like in math. If you have 2 to the second power, it's like 2 squared, which is 4. So you double the concentration and the speed goes up by 4. If you were to take 10 to the second power, 10 squared is 100. So if you raised it by 10 times, the rate would go up by 100 times, etc., etc. In other classes, you might see different orders, but in this class, you're only going to see 0, 1, and 2. So let's look at this reaction, 2 NOs and O2 making 2 NO2s. They found that the rate order for that equals K, rate constant, times NO squared times O2. So we would say that this reaction is second order with respect to NO, because NO has a 2 by it. It's first order with respect to O2. There's not a 1 right there, but it's implied. And also, if you hear about overall rate order, you just literally add up the individual orders. So 2 from NO and 1 from O2, 2 plus 1 equals 3. The overall rate order would be 3 if you hear that expression. In this class, reaction orders 0, 1, and 2 only. So let's talk about what those mean a little bit more. If you have a 0 order reactant, then anything that you have for A, then A to the 0 power will be just 1, and rate equals K. So let's say you were going to double the concentration of A, but A is a 0 order reactant. Well, doubling to the 0 power is 1, rate is still going to equal K. So if you have a 0 order reactant, it doesn't affect the speed of the reaction at all. And we'll come back back to that later. First order is very common for reactants and catalysts in a rate law, and those have a first order dependence. So anything to the first order is itself. So 2 to the first is 2, 10 to the first is 10, etc., etc. So if you would happen to double the concentration of A and its first order, the effect on the speed would be like 2 to the first power. It would be twice as fast. So you double the concentration of A, the speed goes up by 2. You triple the concentration of A, 3 to the first is 3, the rate is going to go up by 3. So that's kind of the idea there. If you happen to have a second order reactant, and they do exist, they're not real common, but they do exist, the rate just goes crazy when you start changing concentrations. So remember that anything to the second order would be like A to the second power. So if you double something, that would be like 2 to the second power, or a change of 4. If you had it 3 times as much, then 3 to the second power would be 9. You'd have 9 times as much. So you'll see huge changes to the rates if you have a second order reactant. So just FYI on that. To find the orders of reaction and then eventually K, what scientists usually do is they'll change the reactant without changing the other reactant. So they'll change like one reactant in a reaction without changing the other reactant. And they'll monitor the effect on the speed or rate of the reaction. If you change just the initial concentration of one reactant, then you can figure out the effect on the rate to figure out the orders. So the first part of this process will be to find the orders of the reaction. And again, for us, it's only going to be 0, 1, and 2. Once you have the orders of the reaction, then the last thing you can do is find the rate constant K. And K is independent of concentrations. It does depend on temperature, as we'll see, but it doesn't depend on the concentration, so that's why we leave it for last. Here's some examples where we have NO2 and CO reacting to make something. Who cares? All right. But I want you to look at what's happening. Up on the right-hand side, we essentially have 3 trials. There's trial 1, which is when the concentration of NO2 and CO are both 0.10 moles per liter, and the rate on the far right, 0.0021. But then we have trial 2. And notice how the NO2 went up by 2 times. It went from 0.10 to 0.20. Likewise, though, the CO concentration stayed the same. It did not change. So any effect on the rate, the value on the far right, will be a reflection of the NO2 on the left. So if we doubled NO2, we went from 0.10 to 0.20. Then we're going to also look at how the rate changes on the right. And you can see that 0.0021 to 0.0082, that's a change of 4 times. So for NO2, you can visualize it then as changing the concentration by 2 to the x, that's the order, we don't know the order yet, but 2 to the x equals a change in the rate of 4. So 2 to the x equals 4, x is going to be 0, 1, or 2, x here has to be 2. And that's how they found the NO2 squared part down there at the bottom. The doubling of NO2 resulted in a rate change of 4. 2 to the x equals 4. X is going to be 2. But let's go on to the next one, because in the 2 versus 3, the third set of reactions, they left the NO2 alone. They didn't change that. You don't want to have any effect from the NO2. But they doubled the CO. CO went from 0.10 to 0.20. And if you look on the right-hand side for the rates, it went from 0.0082 to 0.0083. That's almost a 0 change of the rate. It almost stayed the same. So as you double the rate, the speed stayed the same. That would be like 2 to the x equals 1. And remembering that those little x's, the orders are only 0, 1, and 2, that means that CO here has to be a 0 order reactant. So again, to find these orders, you want to change one reactant and leave all the other reactants alone. And as you change one reactant, you look for the change in the rate. So doubling NO2, the rate went up by 4. 2 to the x equals 4, x is going to be 2. We did the same thing for CO in 2 versus 3. We left the NO2 the same, so there's no effect on the speed from the NO2. On the other hand, the CO went from 0.10 to 0.20. That's doubling it. So 2 to the x in that case equals 1. There was no effect on the rate. X is going to be a 0-order reactant. Once you have the values of the orders, so in this example, we saw that NO2 was second order and CO was a 0 order. And remember that anything to a 0 order is just 1. So in this case, I just totally ignored CO to the 0 power because it doesn't matter. Rate equals K times NO2 squared. And you can use any of those sets of data, 1, 2, or 3, to figure out what K is going to be. So in this example, I used the first set of data, and you can see that the rate in number 1 was 0.0021, NO2 was 0.10 in trial number 1, and we're squaring it because it's a second order reaction. So K equals rate over NO2 squared, rate constant K, 0.21. The units on this particular K would be inverse molar, inverse seconds. So that would be liters per mole seconds. And that's fine if you wish to report the units. A lot of times, though, the convention is just to ignore the units of K. So I would just ignore them. But if you want to, you can absolutely figure it out. Look at the chemicals that go into figuring out the rate constant K and go from there. But hopefully this gets you an idea not only to how to find the orders, but also then how to find the value of the rate constant K. Here's an example. We have a compound called ethanal. Ethanal is an aldehyde. You don't need to worry about that, but aldehydes do sometimes break down. In this case, it's breaking down into CH4, which is methane, and CO, which is carbon monoxide. And we have here some rate law data, all right? And you can see, like before, trials 1, 2, 3, 4, the concentration of the ethanal, the reactant, 0.1, 0.2, 0.3, 0.4. And on the far right, that's the disappearance of the ethanal. That's the rate of how fast it's disappearing. So what we're going to do to figure out this particular rate law in K, we're going to first figure out the rate order of how ethanal is changing. And once we do that, we'll use any set of data. We'll plug in the values to find the value of K. So in this particular problem, what I would do is like what we did in the last example. And notice trial 2 versus trial 1. The ethanal, the reactant, is being doubled. You're going from 0.10 to 0.20. So it's a doubling of the ethanal. And any effect over here on the rate law will be a reflection of doubling the ethanal. And you can probably see that 0.081 divided by 0.020 is roughly a change of 4. The rate is going up by 4 times. Like 0.02 times 4 would be 0.080. It's 0.081. That's close enough. The doubtful digit, the uncertainty, blah, blah, blah is going to happen. So for ethanal, if you want to figure that little order x, it's like doubling it, which is 0.2 divided by 0.1, doubling it to the x power, which we're trying to figure out, resulted in a change in the rates of about 4. 0.081 divided by 0.020 is about 4. And realizing that those little x's, zeros, ones, and twos only, well, 2 to the 0 would be 1, so that's not appropriate. 2 to the 1 power would be 2, and that's definitely not what we saw here. The rate went up by 4 times. But 2 to the second power, 2 squared is 4. So definitely here we have a second order reactant. To formalize this, all right, there's different ways you can do it. Now, these two ways that are described on the left in black and on the right on blue are the two formal ways to do it, all right? You can compare one set of rate data to the other set of rate data. So let's compare on the left-hand side rate 2 to rate 1. And rates, which are the numbers 0.081 and 0.020 for the two trials, they both equal K times the concentration, so 0.2 for rate 2 and 0.1 for rate 1, both to the x power. In this problem, the K's cancel out. K divided by K is just 1. Don't have to worry about it. And 0.081 divided by 0.020 is 4.1. And 0.20 divided by 0.10 is 2 to the x. So if you remember that x can only be 0, 1, and 2, like I said earlier, if x is 0, it would be 2 to the 0 equals 1, and that's not what we see. We see 2 to the x equals 4.1. 2.0 to the first power would equal 2.0, and that's not what we see either. We see 2.0 squared equals about 4.1. So this is definitely a second order reactant. Now in the lab, we're going to use a different method, which is using logarithms. And logarithms can be really helpful here. Notice here, if you do the log of both sides, you get log of 4.1. By the way, this is going right here. So log of 4.1 equals log of 2 to the x. And in the logarithm world, log of 2 to the x can be rewritten as x log 2. So x, which is the order, is going to equal log of 4.1 divided by log of 2.0, rounded up to the nearest number. Log is going to be equal, or x is going to be equal to 2. So either way works great here. Use the way that works fine for you. We're going to use the logarithm method in the lab, but you can use either method is cool. Regardless of which method you use, the order of the reactant, CH3CHO, the ethanal, is 2. All right, so this is a second order reaction. It's second order with respect to the reactant, CH3CHO. In this reaction, we have two NOs and two H2s reacting to make N2 and 2 waters. And this reaction has been determined to be second order in NO and third order overall. What's the rate law for the reaction? Okay, so if it's second order in NO, then we must have a 2 by the NO. And you can see that only answers C and D have a 2 by the NO. A and B, there's no superscript 2 by the NO. Those would be first order NOs. So A and B are flat out, not going to happen. Third order overall means that if you add up all the orders together, it equals 3. So 2 is NO. We don't know H2, but 2 plus whatever H2 is equals 3. That means that the H2 is going to be a first order reactant. So in this case then, if H2 is first order, we would write rate equals K times NO squared times H2 to the first power, or they just leave the first one off. Now, if you happen to pick answer D because of the 2 stoichiometry in front of the H2, this is a good thing to talk about. Those stoichiometries are not necessarily the rate orders. They are sometimes, but not all the times. And we'll talk about this here in a little bit. So rate orders and stoichiometries, not always the same thing. And in this case, they certainly are not the same thing because it's not rate equals K times NO squared times H2 squared. We have instead rate equals K times NO squared times H2 to the first power. And we'll talk about why that is here in a little bit. So use the rate order information. Don't rely on the stoichiometry. So in the last example, we saw that the ethanal, the CH3CHO, was a second order reactant. So rate equals K times the ethanal concentration squared. So it says rate will go up by so much when the initial concentration doubles. Well, if the concentration doubles, that would be like 2 to the second power. The rate would go up by 4 times. And therefore, we would say this reaction is second order. If you put a 2 there, it's second order. If there's a 1, it's first order. A 0 would be 0th order. I don't really like that. I would just call it 0 order, but either way is fine. The last thing we need to do is find the value of the rate constant K. If you look back in the set of data, we started this problem. For experiment number 3, the rate was 0.182 molar per second, and the value of the ethanol was 0.30 moles per liter. At the time, we didn't know the rate order, but the rate order now we know is 2. So the only thing here we don't know is K. So if you want to calculate K, K is 0.182 divided by 0.3 squared, and that comes out to be a value of 2.0. So you can now find the rates at other values of concentrations, etc., as long as you don't change the temperature. If you change the temperature, you change the K, not quite as much fun. Rate laws and rate orders can be super helpful, but most of the reaction that chemists and scientists run into are first order. And as a matter of fact, all biological reactions, all radioactive reactions, and most regular chemistry reactions follow first order kinetics. So if you do some fancy stuff to a first order reaction, you can get out a pretty helpful equation. So in a first order reaction, all right, rate equals K times some reactant to the first order. That's what it means to be first order. They've got a little superscript 1 right there. Well, rate was equal to the change of the concentration over time, and because it's a reactant, we'll put a negative sign in front of it. So negative parentheses delta R over delta time equals K times R to the first power. And if you remember from calculus, if you've taken it, or if you haven't taken calculus, this is something you'll see. It's not important. But if you integrate 1 over R dr, and that equals minus K delta T, or dt, you can get a kind of a useful expression out. Now, if what I just said is gobbledygook, don't worry about it, because this is not a calculus-based class. But if you integrate that thing in red right there, the last line in red, you get a really helpful equation out. And what it comes down to is natural log of R over R0 equals minus KT. And this crazy thing is called the integrated first order rate law. And you're like, oh boy, Dr. Vesa, that's really cool. That's really neat. Okay, this is why it's going to be cool. Because R0 is how much you start with, and R at T is the amount that you have left at time T. So RT over R0 is how much you have left after time T has elapsed. And you can see how the rate constant K fits in there. So the integrated first order rate law has lots of uses. One use is just to find the rate constant K, which can be kind of a pain to find. This is a nice, quick way to find it. If you know how much you started with, R0, and you know how much is left, RT at time T, you can solve for the K, which is a super cool thing. But what's also really useful is, let's say you have a reaction which is really slow. So for example, the half-life of carbon-14, which we'll talk more about in the next section, its time elapsed is just super, super long. It's like 5,730 years for half of it to go away. So that's pretty slow. Well, maybe you don't know how much you started with. You don't know what R0 is. Well, if you have the rate constant K and the time elapsed and you know how much is left, you can back calculate as to how much you started with. So integrated first order rate law is seriously cool. You should know it. We're going to use it a lot, and I'll try and convince you as well how awesome it is, even if right now you don't know. Now, ln is the natural log. In science and math, there's base 10 logs, log, and there's natural logs, ln. And don't confuse them. Like, don't use log logs here, use just ln's. But this is a natural log expression. We'll talk about some math, how to figure this out. On your calculator, you should have an lnx button probably. So if you wanted to find the natural log of a number, you would go natural log, the button, and then put the number in and enter. All right. Probably there's a second function, lnx button, that says a little e to the x. That's called the anti-natural log. We'll talk about that here in a little bit too. A little bit weird, like all of kinetics, I guess, but very powerful. And let me see if I can show you how cool it actually is. So let's look at an example of how to use the integrated first order rate law. And sucrose is a type of sugar, and it breaks down into simpler sugars over time. And this reaction's been studied pretty extensively. Rate equals K times sucrose, and there's not a one power there, but it is a first order reactant. All right, so sucrose is first order reactant. And the value of K at this temperature, 0.21 inverse hours. If we start with 0.010 molar sucrose, it'd be nice to know how long it takes for 90% of it to react, i.e. we have about 10% left, or 0.0010 molar. And this is where the integrated first order rate law can be really helpful. So in this problem, R0, the amount we start with, 0.010, and RT, how much is left, that's going to be 0.0010, and rate constant K, 0.21 hours, inverse hours. So the only thing we don't know then is T, how long it's going to take for this reaction to go. This is where the first order integrated rate law comes in really handy. We're going to use that natural log button, stuff like that. So R0, how much we started with, 0.010. RT, how much is left. We want to know how long it takes to get to 90% decomposition or down to 10%. That's 0.0010 moles per liter. We know that K is 0.21, so the only thing here we don't have is T. So natural log 0.010 divided by 0.010 in your calculator should come out to be minus 2.30. And try that. All right, make sure that you're getting that value, because if you're not, there's something else going on. Like, don't use LOG, use the LN button. But if you get minus 2.30 for that part, you're good to go. And minus 2.30 equals minus KT. K is 0.21 inverse hours. Solve for the time. Time comes out to be 11 hours. So a couple of notes on this problem. First of all, we'll talk about the sig figs of logarithms in Chem 223. Don't worry about it too much. If you use reasonable sig figs, I'm happy. Don't feel like you have to learn all the ins and outs of that. We'll talk about that in Chem 223. Rate constant K and time will always be positive numbers. All right, no question about it. So in this case, K was 0.21 inverse hours, time was 11 hours. They're both positive numbers. And notice the units. If time is in hours, then K will be inverse hours. So if you had a K of inverse minutes, then your time would come out to be minutes. They'll be the same kind of units. They'll be positive numbers, but the K will have inverse time. And finally, the RT over R0, you must use the same kinds of units there too. So we're using moles per liter over moles per liter, which is great. But you can use a lot of different kinds of units there, and as long as they're the same thing, it'll work out really great. So this integrated first order rate law is super cool, and I'll keep showing you examples to try and convince you of that as we go through these particular slides. Okay, so here's a question you might see. We've got some reaction A going to B. Disappearance of A is first order, i.e. we're going to use integrated first order rate law. K, 0.030. We're beginning with 0.36 moles per liter. What will A be after 46 minutes? Okay, so integrated first order rate law, natural log R over R0 equals minus KT. In this problem, we know R0, how much we start with, 0.36. We don't know RT, how much is going to be left. We know that minus KT minus the K is 0.030, and the time is 46 minutes. So notice that time and K are both positive. They're both the same kind of units, like we don't have one in seconds and one in minutes where we have to convert. So we have to solve there then for RT, how much is left. So when you do this problem, it comes out to be 0.090 moles per liter. But I want to focus on the math here just a little bit. So right here, natural log R over R0 equals minus KT, no problem. But we need to get rid of the logarithm. And that's where we use the anti-natural log, which is e to the x. Now, e to the natural log of something, the e and the natural log cancel out. So you can see on the next part then, we just have R divided by 0.36. That's because both of those parts cancel out. But on the other part then, you've got this little e value, e raised to the power of minus kt. Now, little e is just a number. It's Euler's number, I think, 2.712, blah, blah, blah. It's just a constant. You don't even need to worry about it, but you do need to use anti-natural logs. So you'd go e to the power of minus 0.030 times 46 to get the part on the right side. And if you get to 2 sig figs, 0.25, you've done it right. If you don't, let me know. So R divided by 0.36 equals 0.25. R is 0.36 times 0.25. R comes out to be 0.090. If you can do this problem and the last problem, you've got the natural log thing down. All right. It's nice to know how to do an anti-natural log. That's the e to the x. That allows you to get rid of those logarithms when we don't need them in problems like this. So there's lots of use for this integrated first order rate law. You can tell if a reaction is first order based on experiment, which is another thing. Now, most reactions are first order, but not all of them. You also have second order and you have zero order. So if it's first order, rate equals K times N2O5 to the first power. And these are just some different values here. These are values of N2O5 in the second column versus their time on the first part, on the first column. time. So you can see how the N2O5 concentration is decreasing. Reactants are constantly being used up. Now, just bear with me. I'm also determining the natural log of the concentration on the third column. Natural log of 1 is 0. Natural log of 0.705 is negative 0.35, etc., etc. And I'll share with you why I'm doing this here in just a second. If you plot the concentration of N2O5 versus time, it's not very linear. Like you can see there's kind of like a dip in the data. Like the first point and the last point are above the line and the last 2 points are below the line. So we would not call the N2O5 versus time data linear. It's got some other kind of math thing going on. However, if you plot the natural log of N2O5 concentration versus time, you get a beautiful straight line. So we would say that the plot of natural log N2O5 versus time is a straight line. We would call it a first order reaction. And I'll show you why on the next one. So if you're doing a reaction for the first time and no one's ever done it, if you plot the data of the concentration of your reactant versus time, and you see that the natural log of the concentration versus time is a straight line, that means it's going to be a first order reaction. So remember that most reactions are first order, but not all of them. And this is a cool way to verify if it is first order or find out if it's 0 or second order. Now, why that is, we have to delve a little bit into the logarithm world. And if you look in the upper right-hand side there, there's a trick you can use with logarithms. Natural log of x over y is equivalent to the natural log of x minus the natural log of y. And we're going to use this trick. So in our first order integrated rate law, natural log of a over a0 or r over r0, whichever one you want to use, that equals minus kt. And you can rewrite that as natural log of a minus natural log of a0 equals minus kt, and then place the natural log of a0 on the other side. You get this expression, natural log of a at time t equals minus kt plus natural log of a0. And you're like, oh boy, Dr. Russell, that's really cool. What's so exciting about that? Well, that's an expression for a straight line. And if you remember from the graphing lab we did, or if you've taken this stuff in math before, a straight line can be expressed as y equals mx plus b. And m in that expression is the slope, and b is the y-intercept. So if you plot on your y-axis the natural log of the concentration values, and on the x value you have time, you should see a straight line. And the slope will equal minus k, which is kind of cool. And the y-intercept is the concentration of your reactant at time 0, like how much you started with. And this is super huge for science because, wow, if maybe you don't know how much original material you had, hey, no problem. Plot the natural log of concentration versus time. And if you go to the y-intercept, you can figure out what it is. Also, finding the rate constant can be kind of tricky. This provides a really nice way to find the rate constant. The slope equals minus k. So if you take minus the slope, it'll give you a positive number. Rate constants k are always positive, like we said. Great way to find the rate constant. So all first order reactions, which is everything in biology, everything in radioactive chemistry, most of regular chemistry too, all of those reactions will give a straight line if you plot natural log of r versus time, which is really cool. Now, in case you happen to have one of the other types of order, second order or 0 order, you will also get a straight line if you plot 1 over the concentration versus time. That's a second order test. And if you plot just concentration versus time and get a straight line, that's going to be a 0 order test. And in the handout and on the next page, I'll talk more about this. But anyway, it's a pretty cool use. It's a great way to find the rate constant k. It's a great way to find how much material you started with. Remember that rate constants k are always going to be positive numbers. Slopes will come out to be a negative number. You need to take the minus the slope to find the positive k value. Good to go. Here's an overview of the three different types of rate constants you can see. So the top one is zero order, middle is first order, second one, the last one there is the second order. Let's look at the middle one, the first order, because that's the most common one. So rate equals k times a, and you don't have to put the little superscript 1, but it's not bad to do that. That's what you're going to do. And if you plot this then, natural log of the concentration versus time, you should see a straight line, which is really cool. Slope equals minus k, y-intercept equals the natural log of the concentration. There's also something called half-life we'll talk about in a little bit. There's a nice way to find half-life from k or k from half-life, and we'll talk about that. The other ones, the top one for zero order and the bottom one for second order, are helpful too. If you have a brand new reaction you're looking at, you should do a test to see which order it behaves. And most of these orders will be first order, but just to make sure, you should do zero order tests and second order tests, and we'll talk about this in the problem set. This is the kind of question you might see. It says the graphs below were obtained for a chemical reaction, and it wants to know what the order with respect to the rate law is. And you can see how the first graph is concentration versus time, the second graph, natural log of concentration versus time, and the third graph is 1 over concentration versus time. And it wants you to know, well, first of all, D doesn't make any sense, not enough information, because of course this is what we've been talking about. So anyway, what you want to do is you want to look for the best straight line, all right? And the best straight line in those three graphs is certainly the third one, 1 over concentration versus time. So that's definitely a linear relationship. The other ones have some kind of curve associated with it. So if it's 1 over a versus time gives you the best linear fit, 1 over a versus time, that's a second order existence. So we would say that this reaction is a second order reaction, and we're good to go. So in the last slide, there was a little bit of information on the half-life, and half-life is actually another really important concept when it comes to the different rate laws you can see. So let's talk about what half-life is first of all. Half-life is literally a time, so it'll be a value in seconds, minutes, hours, something like that, and it's the time it takes for half of a sample to disappear. So that means that half of the sample has reacted, if you will, and half of it is left. And for first order reactions especially, half-life is very, very helpful. So on the graph there on the right hand side, we're talking about hydrogen peroxide, H2O2, and we're starting at 0.020 moles per liter at the top. And you can see what they're doing. They're plotting then the amount of time, which is the x-axis, the amount of time it takes to go to 1 half-life. What that means is the concentration goes from 0.020 to 0.010. Then it takes another half-life to go half of that value, so to go from 0.010 to 0.0050, etc. And the half-life should be the same. So half-life is really an interesting idea. What's important to realize is that 1 half-life, you're down to half the sample. It's not 2 half-lives to get to 0 sample. 2 half-lives would be half of the half you were left with, or 1/4 of the original amount. And another half-life would be 1/8, 1/16, stuff like that. So it's kind of crazy. In theory, you never get to 0, all right? And that's a little disturbing. If you have something radioactive, you're going to have less and less and less and less and less, but will you get down to 0? Probably not. But half-life does have a lot of cool uses, and we'll talk more about this as we go through this section. Hydrogen peroxide has a half-life of 654 minutes. So if you start again with a 0.0200 molar solution, in one half-life, or 654 minutes, you'll be half of the reactant remaining. So you'll be down to 0.0100 molar. After 2 half-lives, that doesn't go to 0, you'll be half of the 0.01 number, you'll be down to 0.0050 molar. And after another half-life, then you're down to 0.0025. So you can see how you went from 0.02 to 0.0025 there in just 3 half-lives. However, it's not to 0, and that's what's really important. So we would say the half-life for hydrogen peroxide is 654 minutes. And you could convert this to seconds if you want. You could multiply by 60 seconds per minute to get the half-life in seconds. You could also convert it to hours. You could divide 654 minutes by 60 minutes per hour to get hours. Any kind of units are fine, and you can adjust them as you need them. Half-life gets that symbol T1/2, so if you see that, that's what it's referring to. Sugar, like most biological processes, is a first-order process when it ferments, and sugar and the enzyme make some kind of products. And the rate of disappearance of the sugar, it's a first order, rate equals K times the concentration of the sugar to the first power, and rate constant K 3.3 times 10 to the minus 4 inverse seconds. So the question is here, what's the half-life of this reaction? And this is kind of a problem you might run into. Now, to answer this, what we're going to do is we're going to go back to the first order integrated rate law, where natural log of R over R0 equals minus KT. However, before we do that, R over R0 is going to equal 1/2 when we're at half-life. So if you started with 5 moles, you'll be down to 2.5 moles. If you started with 1 mole, you'll be at half a mole. But whatever you start with R0, R will be half of that number when you get to the half-life. So R over R0 equals 1/2 when the time equals half-life, T1/2. So if you rewrite natural log R over R0 as natural log 1/2, that equals minus KT, but T at this point is the half-life, T1/2. So you can see what's happening here. We've got natural log of 1/2 essentially equals minus K times T half-life. Now, natural log of 1/2 is minus 0.693 in your calculator. So minus 0.693 equals minus K times T1/2. And if you clean that expression up, half-life, T1/2, equals 0.693 divided by K. And this is pretty cool for chemists. So in this problem, the K value, 3.3 times 10 to the minus 4, we can find the half-life easily. 0.693 divided by the K value, 2100 seconds. And if you divide that by 60 seconds per minute, you'll get 35 minutes. So anyway, a couple of things about half-life. Half-life is time, all right? Just like rate constant, it's going to be a positive value. You have to have the same units for K and half-life. So in this problem, K was in inverse seconds. That means half-life will be in regular seconds, all right? If the K would have been inverse minutes, half-life would have come out to be minutes, stuff like that. So here's another problem. For a given first-order reaction, K equals 0.347 inverse hour. What's the half-life of this reaction? So K equals 0.693 divided by half-life, or half-life will be 0.693 divided by the 0.347 K value. But the value you get initially is going to be in hours, because remember, K and T have the same kinds of units. So the half-life you initially calculate will be in hours. All of those answers are in minutes, so we have to convert then hours to minutes. So in this problem, once you convert half-life, 0.693 divided by 0.347, the answer comes out to be hours, and you need to multiply the hours by 60 minutes per hour to make sense with the answers you're given. So if you do all that, it comes out to be 120 minutes, and we're good to go. Now, personal apology, I used to play a game called Half-Life a lot, and in Half-Life, there was a character, Dr. Gordon Freeman, and this is the last answer there on E, and that little blurb right there is just a memoir of all the good times I spent in that game. But anyway, that's really nothing you need to worry about. It has nothing to do with what we're talking about. But when I think about Half-Life, all right, I think about this game. Yes, I need therapy, I know. But anyway, hopefully you understand half-life, K values, blah, blah, blah. Here's another kind of question you might run into. We've got the same kind of problem, got the sugar, got the K value, 3.3 times 10 to the minus 4, half-life, 35 minutes. We just calculated. We're starting with 10 grams of sugar. How much is left after 2 hours and 20 minutes? Okay? And this is a kind of problem that can be answered in two different methods. I'm going to talk about one method, which is the Chem 104 method, and I'm going to talk about the better way, which is what I'm going to call the Chem 222 method, okay? Now, in Chem 104 and the lower chemistry classes, how we would answer that is we'd figure out how many half-lives elapsed in 2 hours and 20 minutes. So because 2 hours, an hour is 60 minutes, so 2 hours would be 120 minutes plus 20 minutes, 140 minutes total. And the half-life, as we saw in the last problem there, 35 5 minutes. So the total time divided by the half-life time gives you the number of half-lives, 4 half-lives in the Chem 104 method. So what you can do, if you're starting with 10 grams, after the first half-life, you'll be at half that, 5 grams. Second half-life, 2.5, 3, 1.25. Fourth half-life, you'd be down to 0.625 grams. And that way does work, especially if you have an integral whole number of half-lives that have elapsed. But a much, much, much better way to do this is to use the first-order integrated rate law. Now, a couple of things about this. K is in inverse seconds, and we have hours and minutes. So you have to convert hours and minutes into the same kind of units as K. So 140 minutes, which is what we saw earlier, times 60 seconds per minute, that's going to give you 8,400 seconds. That's going to be the T value here. And we know that R0, how much we start with, is 10 grams. We have the K value. We just calculated T, so the only thing here we don't have then is R, how much is left. So if you go through the math, natural log of R over 10 equals minus KT, and then you have natural log of R over 10 equals minus 2.772 when you multiply those together. Now you need to use the anti-natural log. That's the little e to the x button we've talked about earlier. That gets rid of the log on the left side, and e to the minus 2.772 is 0.0625. So if you multiply that by 10, that's going to give you the amount left after this long, 0.625 grams. Now, why I like this method better and why I encourage you to use this is you can have any number of half-lives. It doesn't have to be a whole number, and you can automatically calculate how much is left. Now, you do have to use anti-logs. I understand that's not a lot of fun sometimes, but it's all stuff you can do. Let your calculator do the hard work, and you are good to go. So I do recommend using the Chem 222 method, quote unquote. You're not limited to the whole number of half-lives. It's pretty chill. Again, that e to the x, that e is just a constant. It's called Euler's number, 2.71828. It goes on for a long time like pi. Nothing you have to do. Let the calculator do this work and you will be good to go. As I stated earlier, all radioactive processes, as well as all biological processes, as far as I know, follow first-order kinetics. So first-order kinetics and this first-order integrated rate law and half-life become super important when it comes to radioactive decay, which we'll talk about more in the next chapter. So here's an example of this. You can have tritium, which is a radioactive isotope of hydrogen, decompose into an electron and a helium-3 nucleus. And if you start with 1.50 milligrams of tritium, how much tritium would you have left after 49.2 years? And the half-life for this process is 12.3 years. We'll talk about this kind of reaction in a future lecture. What I would do here, I would use, once again, you know it, the first order integrated rate law. Now we don't know R, how much is left, but we know that R0 is what we start with, 1.50 milligrams, and we want to know T, how much is left after 49.2 years. But we don't have K. So right now we have one equation with two unknowns, R, how much is left after that long, and we don't have K. However, the half-life allows you to find the K value pretty easy. K equals 0.693 divided by the half-life, and if you do that, that's 0.0564 inverse years. Now again, make sure that your K value, your half-life, and the time elapsed are all the same kind of units. So in this case, we're using all years. You wouldn't want to use years and months and days or something like that. They all have to be the same kind. K will be inverse time, but it still has to be the same kind of unit. So anyway, natural log R over R0 equals minus KT. We've got all the pieces we need now. The minus KT part comes out to be minus 2.77. You can do the anti-log of that to get rid of that. That's the Euler's number once again. Make sure you know how to do this, 0.0627. And if R0 is 1.50 milligrams, then R is 1.50 times 0.0627, we have 0.0941 milligrams left. And this is kind of cool because who wants to wait 49.2 years for something to happen? Not me. I can't even wait in line at, the store. But anyway, that's a personal problem. Anyway, this is a quick way then to find the time elapsed without having to actually be there, which is really powerful. And in terms of our human lifetimes, some of these times elapsed will be huge amounts of time. You couldn't wait, but we can calculate it because we've modeled it with physics and math and chemistry. Oh, yeah. In this problem, we have a copper-64 isotope, which is radioactive. Apparently, it's used in studying Wilson's disease. Anyway, the half-life here, 12.70 hours. What fraction of copper-2 acetate remains after 2.0 days? Fraction problems with radioactivity means what's R over R0? All right, that's kind of what it's trying to ask for here. And we have here a half-life. We have here a time elapsed. So natural log R over R0, which is what we're trying to solve for, equals minus KT. We don't have K, but we have a half-life. So we'll turn the half-life into K times T, natural log R over R0 equals minus KT. We can go from there. So if you do the math, 0.693 divided by 12.70, the half-life, that's going to give you the K. I didn't even calculate it in this problem. I just threw it in the problem and multiplied it by 48 hours, which is 2 days, by the way. I forgot to say that, but remember, all these things have to be the same time system. So R over R0 will be the anti-natural log e to the power of minus 2.6192. We're going to have a fraction left, 0.073. So kind of cool to figure these things out. Half-lives for radioactive substances are all over the spectrum in terms of time. Uranium-238 has a half-life of 4.5 times 10 to the 9th years. So 10 to the 9th is a billion. That's going to be 4.5 billion years. And of course, nobody's sticking around that long to measure that. So thank you, science and math, for letting us do this. Carbon-14 is actually pretty helpful to scientists. Carbon-14 has a half-life of 5,730 years. And then you can see iodine-131's half-life. That was released into the air around Hanford in eastern Washington back a couple decades ago. Not the best. Element 106 is one of the newest elements. It's seaborgium. Seaborgium has a very small half-life, 0.8 seconds. So imagine you have 1 gram and you want to show a friend. Well, basically 1 second later, you're down to half of your sample, which probably wasn't real big to begin with. Crazy. But element 111, Roentgenium, named after the X-ray scientist, has a half-life of 0.0015 seconds, so very, very small. So anyway, just realize half-life is a powerful concept. Half-lives can be super long, super short. Wow. Half-life of caffeine is something that I find personally relevant because I drink way too much coffee, but that's not my problem. They claimed the half-life of caffeine in our body, 3.5 hours. So that means if you consume some caffeine, 3.5 hours later, you're down to half the caffeine. Another 3.5 hours, you're down to half of the half, et cetera, et cetera. Medicine is also a field that uses half-life as well. You can have half-lives for other types of expressions. We're mostly focusing on first order here, where half-life is 0.693 divided by K, and that's by far the most useful. If you ever do a second order half-life, you have to take into account the initial concentration, A0, and that's another thing we won't talk about here, but it is something that can be calculated. Zero order also has a concentration dependence on the initial amount you start with. So anyway, first order, it's especially useful to have half-life values because it allows you to find K directly. When you have second and zero orders, you need to know the initial amounts. Not quite as handy, but it can be cool.